Bismillahirrahmanirrahim. We are going to start this course, Group Theory. I have already uploaded Group Theory for beginners, and this is today is the first lecture, and we are going to talk about the introduction to the groups. And to talk about that, what can we do is to start with this. So, Group Theory comes from combines four actually different subjects, and there are applications, there's a usage of all these subjects inside group theory. So we are going to see. So in group theory we have classical algebra, which was started in 1770 by J.L. Lagrange by working on the polynomial equations. Then we have number theory, which was started by C.F. Gauss uh, in started it with his work Disquisitions Arithmetic in 1801. Then there is a presence of geometry inside group theory, and this was started by F. Keeling in the lecture A Comparative Review of Recent Research in Geometry in 1872. And he actually gave that lecture, and then it started how we can use the geometry inside group theory or for the group theory. Then there is also a usage of analysis, the real analysis or functional analysis things inside the group theory, and this was the originators of this source was S. Lee, the Lee theory, kind of a person, which is who has started in 1872, and H. Poincare, which is there is a conjecture, famous conjecture, Poincare conjecture, and that's the same one. And then there is F. Kalin again, who has started in 1872. So let's start how we can understand group theory by something which we already know. So there are some quotes for the motivation. So symmetry is a powerful guiding principle that has been used in creating these models for quantum physics. The more symmetrical a model is, the easier it is to analyze. So that's why we are very much interested in group theory, because in group theory we always talk about the symmetries. It's, you can say, it's a study of, it is the study of symmetries. Now symmetry is a vast subject significant in art and nature. Mathematics lies at its roots, and it could be hard. It would be hard to find a better one on which to demonstrate the working of the mathematical intellect. Now, particularly talk about groups, I want to first introduce the symmetries of square. So we can introduce the symmetries of square by, let's draw this square, this is the simple square, and then we can say, then we can rotate, we can keep it same, and that will be the rotation of 0 degree. Then we can rotate it up to 90 degree, and this rotation is counterclockwise. So that will convert this square, this square into this one, and then we can talk about the rotation of 180 degree, again the counterclockwise, and this rotation so converts this is first square into the second one, and you can see these edges are actually moving when you are rotating, so they are creating a different motion. Similarly, we can continue and say rotate it up to 270 degree, and that will create this one. Then if you consider the square which we had for the like previous square, simple one like the original one, that is this one, and then if you flip it on the horizontal axis, that will again be called as that will again be considered as a motion, and that flip will do is to shift all the above edges to the below, and then below edges to the above, and then we can also flip it at the vertical axis, and that will do PG WB to WB PG, and then we can do four two more flips, but these flips are going to be on the diagonals. So let's fix the main diagonal and then flip other two, and that will give us this one. And then let's fix the other diagonal and then flip the main diagonal element edges. We will get this square. So all these eight motions are the symmetries of the square. Now, by the fact that every motion is equal to one of these eight listed in figure 1.1, that means that if you try to flip the square any more times or any number of times, you will again end up with inside these eight motions. So suppose a square is repositioned by the rotation of 90 degree, followed by a flip about the horizontal axis of symmetry, then this will be the square. We rotate it up to 90 degree, and then we did a flip. Then we will end up with this square, and that will be equal to d. Thus, we see that this pair of motions taken together is equal to the single motion d. Now, this suggests that we can compose two motions to obtain a single motion. But remember that the order of the composition is very important, and you have to be careful when you are composing these motions, because if you compose H and R90 or R90 and H, you will, if you compose R90 and then H in a different way than this, you will end up with different motion. Now, the eight motions are 0 or 90 or 180 or 270, H, V, D, and D prime are considered as functions. You can also say these are permutation functions or simple functions. And together with the operation composition, we form a mathematical system and we call it the Heidel groups of order 8, because there are eight number of motions. So the Heidel group is of order 8, and we denote it by D4. So for general n motions, we denote this group by Dn. Sometimes people denote it by D2 power n, but let's fix it there. Now let's look at some properties of groups by the way of example D4. To do that, we construct an operation table. We call it operation table or the Cayley table. Cayley was English mathematician named Arthur Cayley who first introduced these tables in 1854. Now let's construct this Cayley table for D4 below. So this is a Cayley table. If you look at this Cayley table, then you can analyze actually that this table have these motions in a horizontal way and in a vertical way, and then you are composing them like this from here to here, from here to here. And to do that, you can see that R naught or 0 is going to fix every single motion in horizontal line and in vertical line. And the motion we did previously, where we composed H and R90, that produced D. But when you are composing R90 and H here, you are getting D prime. So the order of the composition is very important. Then you can have a square, draw a square on a paper, and try to compose, try to rotate or flip on horizontal axis, on vertical axis, on the main diagonal or other diagonal. These are all the motions. And then when you are composing, try to do the first operation that could be any rotation or any flip, and then try to do other. If there is rotation or the flips, you will end up with inside this table. So this is the power of the Keller table. You will not be able to go out of this table. You will always end up inside this table. And if you are doing the composition in a right way, in a right manner, you will always get these values. Okay, perfect. Now we know that by the above fact that every sequence of motions turn out to be one of these eight. So algebraically, we know we call this closure property, and that can be defined as, let's consider A and B and elements from D4. Then if you compose any two elements or any three elements or any number of elements, just for the sake of closure property, we take two and then we compose them. We will again end up inside D4. And this property is called closure property. Okay. Now, if you take any element A from D4, then if you compose it with R naught or you compose R naught with it, you will end up with the same element A. That means the element R naught is called an identity, and every group must have one identity. That is the condition. Perfect. Now for each A inside D4, there is exactly one element inside D4. So B, such that if you compose A and B or B and A, you will get R naught an identity. Okay, so this means B is said to be an inverse of A and A is said to be an inverse of B. Now, for example, R90 and R270 are inverses of each other, and H is its own inverse. Observe that the composition HD is not equal to DH, but the composition of R90 with one R180 or R180 with R90 is similar. They are both same. So, in a group, it can be possible that AB may or may not be, for two elements of group A and B, it is possible that they are may or may not be same as BA. If AB is BA for all the choices of group elements A and B, we say that the group is commutative, or it is also known as abelian. And the name abelian comes from the great Norwegian mathematician Niels Abel. Niels Abel, so the field medal which people get in mathematics is known as Abel Prize, and that is the same person. That medal is after this person, Niels Abel. Thus far, we have illustrated by way of D4 three of the four conditions that define a group. Namely, we have talked about closure property, we have talked about existence of an identity, and we have talked about existence of inverses. The remaining condition required for a group is known as associativity, and that is AB multiply C is A multiply BC for all A, B, C inside the set. Now, to be sure that D4 is indeed a group, we should check this equation ABC, this one, possibly for 8 power 3 choices for ABC inside D4. Because there are 8 elements inside the group and we are choosing 3 elements. So there is 512 possible choices. But nobody actually check this property because this is true for default. Okay. Now let's particularly talk about in general about the dihedral groups, where they occur or what can we do? How can we get them? So a dihedral group, so by the analysis we carried out above for a square can be similarly done for an equilateral triangle or a regular pentagon or indeed any regular n-gon where n should be greater than or equal to 3. The corresponding group is denoted by Dn and it is called the dihedral group of order 2n. The dihedral group arise in art and in nature. So many designs, like the decorative designs used on floor coverings, pottery, and buildings, have one of the dihedral groups as a group of symmetry. Now let's talk about where they occur. So the, the Chrysler's logo, there is this Chrysler's logo, you can Google it, has D5 as a symmetry group. The Mercedes-Benz, the famous Mercedes-Benz has D3, which is also isomorphic to S3. And I'm going to talk about these, how two groups are going to be isomorphic is S3. So the Mercedes-Benz have this D3 as a symmetric group. The ubiquitous five-pointed star have a symmetric group D5. The phylum Echinodermata contains many sea animals like starfish, sea cucumbers, feather stars, and sea dollars that exhibit patterns with D5 symmetry. In chemistry, chemists classify molecules according to their symmetry. Moreover, symmetry considerations are applied in orbital calculations, in determining energy levels of atoms and molecules, and in the study of molecular vibrations. Okay, so the symmetry group of a pyramidal molecule such as ammonia NH3, which has one nitrogen and three hydrogen, depicted in figure 1.2, have the symmetry group D3. And in similar way, you can talk about more of them. So you can look at any shape, anything inside in the nature, and then if you see some symmetry, then they must have some dihedral group. So okay, I will end this introduction lecture over here, and then in the next part, in the next lecture, I'm particularly going to define the group definition and its properties, and then probably the subgroup. Thank you so much. Hope you enjoyed it. And if you have any questions, you can tell me in the comments. Thank you.